This is the second lecture on probability, and in this lecture I'm going to give just a basic notation for calculating probabilities. Mendenhall does this sort of in section 3.2. You can use, I'm using his notation, or you can look there also for the notation, but I think the way that I'm giving the probabilities formulas is easier here, and I think it makes more sense than the text. There's some basic vocabulary for probability. The first is what's called the outcome. Rolling the die, rolling, drawing cards from a deck of cards, flipping coins, those are called experiments in probability. And the outcomes, that's a list of all the possible results that you can get. You put those all together, and that's called the sample space. For example, what are the outcomes for flipping a coin? They're heads, tails. Okay. Um, you have to know all these outcomes in advance in order to do these problems. And the set of those all together makes up the sample space. So here are some examples of sample spaces. Let's say you're going to flip a coin 2 times, and that's going to be your experiment, 2 flips. Okay, what could turn up? Heads, tails, tails first, then heads, 2 heads, and 2 tails. There's your sample space. That's all the possibilities of what can happen flipping that coin 2 times. Let's say you have a family with 3 kids in it, and so you're going to list whether you've got girls or boys and what combination there are. You could have 3 boys, you could have 3 girls, or you could have it in other different orders and different amounts, 2 girls and a boy, and look, they can occur. Girl could be first here, the boy's first here, etc. So all those combinations, all those possible combinations, that gives you your sample space. And rolling one die, it's 1, 2, 3, 4, 5, 6. That's it. Say you have a box of 5 resistors, and you got 2 bad ones in there. So that's simple. You could have 2 bad ones right at the first, 2 bad ones right at the end, or they could be scattered out throughout the box. Now, an event is a subset of the outcomes. That's of all your outcomes in your sample space, you'll select something to try to find out its probability. For example, say you're rolling 2 dice, okay, and you want to find the probability that the sum of the faces of these dice is going to come up, of the 2 dice, is going to sum to 6. So how many possible outcomes do you have rolling 2 dice? If you roll 1, you've got 6. But if you roll 2, you can put it in a table like this, or there's other ways to compute it. So here's what's showing up on the face of 1. Here's what's showing up on the face of the other die. So when you add those together, you find out there's 36 possible ways they could be added together. And so your sample space has 36 outcomes in it. That's what I have up here. Okay, now how many sum to 6? Well, this one does. I put them in bold so I could find them faster, and you too. Okay, those are the ones that sum to 6. There's only 5 of them. That's your event. The event is summing to 6, and there's 5 possible ways that can happen. There's something called a simple event, and a simple event is one in which there's only one way it can happen. For the die, if you're rolling 1 die and you want it to come up 3, that's a simple event because there's only one way that 3 can happen. If you're flipping a coin, or just 1 time, say, and you want to know, the heads, the fact that heads show up, that's a simple event. Okay. So we're going to call the probability, we'll define it as the likelihood that the event will occur. And as we discussed before about the difference between the frequentist approach and the Bayesian approach. But we all have to start at this point anyway, no matter what approach we're going to take later. Okay, so this will be the likelihood that the event will occur. And you give it as a fraction, a decimal, or a percent. So we're going to start with the assumption that every outcome in the sample space is equally likely. Right? And we're going to calculate the probability for that event occurring. And here's a formula which I mentioned a little bit in the first lecture. To find the probability of an event occurring, you take the number of ways that event can happen and you divide by the number of outcomes that are in the sample space. I think that's a pretty simple formula, and it's fairly standard. Mendenhall starts with a bunch of simple events, and then from that somehow gets to this, and you can follow that reasoning too. So let's look at a simple event. We have the same formula that we did before. We take the number of ways that the simple event can happen, divide by the number of outcomes in the sample space. Since there's only one way that a simple event can happen, this is just 1 over the number in the sample space. So here's a bunch of examples. We had before throwing a pair of dice and wanting the sum to be 6. There were 5 different ways that could happen. So the number of ways that can happen is 5. The total number in the sample space is 36. The probability is 5 divided by 36, which comes out to be about 14%. We had a family with 3 kids in it. The probability, or the number of events, the number of events in which the boy is the first child is a boy, that would be 3 boys, 2 boys and a girl, boy, boy, and boy, girl. Okay, there's 4 of them. So the number of ways the event of having a boy first can occur is 4. The number in the sample space is 8. You divide them and come up with 50%, which you would have done by reasoning too. Let's say you want to draw an ace of spades from a regular deck of cards. Okay, a regular deck of cards has 52 cards in it. There's only one ace of spades, so the probability is 1 over 52. What if you want to just draw an ace? You don't care what the suit is. There's 4 aces, so the probability is 4 over 52. So here's the basic rule of probability, which can also be used in calculations. And this rule is that probability can vary from 0 to 1, or in percent, it would vary from 0% to 100%. The probability is 0 for an event that can never occur. For example, if you want the sum of, you're rolling a pair of dice and you want the sum to be 14, that can never occur, so the probability is 0. If you want to draw 3 of a kind from a deck of cards and you want all 3 of them to be red, no, that can't occur. Its probability will be 0. The probability is 1 if the event has to occur, no matter what. For example, if you're flipping a coin and you say, what's the probability it will be either heads or tails? Well, its probability is 1 because it's going to be either heads or tails. So anytime you calculate a probability and it's greater than 1 or less than 0, you need to go back and look at that again because something's wrong. Now, if the outcomes are not equally likely, you can't calculate the probability based on that formula. In fact, you have to be given that information, right? But no matter what, the sum of all the probabilities must still equal 1. For example, if somebody files a little bit on a die and makes it so they say it's loaded, but generally it's filed, okay, so that one side is more likely to come up than the others, then the fact that one comes up more frequently means the others come up less frequently, so their probabilities have to be adjusted. Here's another example. Say you have that box of 5 resistors in it, and you know that 2 are broken. Let's say you had say they were put in there, they were fine, all the resistors are fine, but the box that puts the machine that puts the box together squeezes them too much and breaks the first and the last one. Right, so the probability that the first and the last are broken is going to happen all the time because the machine is defective, so that's a 1. What happens to the probability of all the other occurrences? They have to be 0 because the sum of all these probabilities over the sample space has to be 1.